Let's see how our types work out on this example. We've got a function f, and it expects a record r. That record r needs one field p, and that field p needs to map to another record that has an x field mapped to int. And now inside the function, we call r.p.x. Overall, this should give us back an int. Suppose we call this function with a record p that maps to a record that has an x field, but then also has a y field. Intuitively, this application should be well typed. Our function expects an argument with this blue type, and we've passed in this green type that has extra information. But the way we've written our subtyping relation, this is not allowed. Our green type would get rejected. Let's look again at the rule. The reason that p with x, y inside is not a subtype of p with just x inside is because in our premise, we're asking for two equal types on the matching fields. If we were to write this all out, we would see that when we get to the p field on the outer record, we're looking for two equal types on the inside. But what we have is x mapped to int, y mapped to int, and x mapped to int. And those are not exactly equal. The fix here is to relax our field comparison. Instead of equality, we want to use the subtyping relation on those field types. What if we have an update? Here, the function takes in a record r, and then it updates that p field to map to a record that has an additional field on the inside. P has the type x mapped to int, and then we're adding a value that has x mapped to int, but also y mapped to int. As things stand, this application would get rejected, and that's because our typing rule for field update is looking for an exact match. The type for E2 has to have a type that's inside the record. We can fix that by revising the rule. So E2 can have any type tau prime, as long as T prime is a subtype of the matching field's type.